Okay, so what we're going to do now is we're going to actually learn how to solve the differential equation that describes the charging of a capacitor. Let me remind you where we are. We're talking about a circuit that has a battery, some electromotive force epsilon, and that battery is pushing charge through a resistor and a capacitor. And we analyzed this circuit, walking around it, and we turned this circuit into a differential equation. What's it a differential equation for? It's a differential equation for Q. Q is a function of time. Q is the charge on this plate of the capacitor. And dQ dt, that's another way of writing the current. So dQ dt here, this is the current through the capacitor. Q itself is the charge on the positive plate of the capacitor. And by analyzing this circuit, we reach this differential equation. Now what we're going to do is we're going to take a math interlude. We're going to learn how to solve this differential equation. We will come back to this as a piece of physics in a minute, but we're going to just look at this as a differential equation. So what do I see here? I see dq dt is equal to some constant, and then here's the function itself, and then here's some other constant. So I want then to analyze this differential equation, and the way I'm going to do it is I'm actually going to start with an even simpler differential equation. It turns out that in 802 you don't need to learn the solution of differential equations in the full way that you would in a course on differential equations. It turns out that everything we do in 802 that needs differential equations is really going to be built on two different differential equations only. And the first of them is the differential equation that you get if you cover up this constant here. So it's dq dt is equal to minus some constant times q. That's the first differential equation we need to know how to solve. And there will be one more a little bit later. But everything we need to analyze this circuit comes from that differential equation. So I'm going to pause, erase the board, and we're going to start doing some math. I'm going to take a little interlude and just do math and learn how to solve the simple version of this differential equation in which there's no second constant here. Okay, so as promised, a math interlude. This is the equation that we got from the physics and that we want to work up towards solving, but we're going to start with a simpler equation. And to emphasize that this is a math interlude, instead of calling the variable q, I'm just going to call it a, because in this equation here, this is going to be related to the equation that I want to analyze. But this equation here is just a math equation. And instead of calling the constant RC, I'm going to call it tau. And I'm going to start by analyzing this math equation. So what does this equation say? First thing, when you run into an equation like this, you have to keep track of what's a constant and what's a variable, and what's a function of what. So a here, this a, which occurs on both sides of the equation, this is a function of time. Excuse me. This is a function of time t. So a is a function of time t. Okay, so what's this here? This is a constant. Anytime you see a constant, ask yourself what its units are. How can I tell what its units are? I don't even know what a is. A is just something in math. But look, I have an a here on this side and an a on that side. So whatever this a is, whatever its units are, its units cancel between the left side and the right side. So whatever tau is, it has the same units as t. So it's a constant with the units of time. And in a rather unimaginative choice of name, this constant is called the time constant. So this is a differential equation. I want to solve it. I'm going to solve it by the method of me telling you the solution and then you helping me check that I got the right solution. If this were a course on differential equations, we would build much more fancy apparatus to learn how to solve a differential equation. Why would we do that? Because we'd want to solve lots of much more complicated differential equations. This is a very simple differential equation. The best way of solving this is to write down the answer and check it. So here we go. I'm going to write down the answer for you. So the answer is that a as a function of time is given by a naught, and I better tell you what a naught is, e to the minus t over tau. And this a naught is a constant that I get to pick. So before I pick the constant, I want to check that this really is a solution of this differential equation. You should be doing this yourself while I'm talking. I claim that this is a solution of that equation. You should be checking even before I do. So how do I check that? So this is the check. So I take this A and I differentiate it, and I see what I get. I take this A and I differentiate it. Well, A naught is a constant. I differentiate e to the minus t over tau. I get minus 1 over tau e to the minus t over tau. And then I notice that A naught e to the minus t over tau is just A. So this is equal to minus 1 over tau times A. And that's what it was supposed to be equal to. So this really is a bona fide solution to this differential equation for any choice of this constant A0. And I then notice that A of time t, A at time t is equal to 0 is equal to A naught. So the interpretation of this A naught is that A naught tells me the value of this function at time 0. And with that value specified, the solution to the differential equation tells me what this function looks like at all times. And that's the math. Let me make a graph or a sketch of this solution to this differential equation. So I'm going to graph A as a function of time t. And so here's time 0, here's time tau, here's time 2 tau, here's time 3 tau, here's time 4 tau. And at time 0, what's A of t? Well, at time 0, it's equal to A naught. And at time tau, it's, well, at time tau, when t is equal to tau, it's A naught e to the minus 1. 1 over e is about 0.37. So by the time I get to time tau, this function has dropped all the way down to about this value. By the time I get to 2 tau, it's A naught times e to the minus 2. That's 0.37 squared. So it's fallen by another factor of 1 over e. And then it's fallen by another factor of 1 over e. And what I get here is a classic exponentially decaying curve which asymptotes towards 0 exponentially fast. And this is my function A of time. It's an exponentially falling function, and it starts at A naught, drops exponentially, and what tau is, the constant tau in the equation, came from here, the constant tau in the equation, which we call the time constant, that tells us that after 1 tau, A has dropped by a factor of 1 over e. After 2 taus, A has dropped by a factor of 1 over e squared. After 3 taus, A has dropped by a factor of 1 over e cubed, etc. So this is the conclusion of the first half of the math interlude, because this differential equation is not yet the same as this differential equation. So now I want to write a differential equation that is very similar to this, but not exactly this, and it'll be directly related to this one. Let me write a differential equation down for some function b of time. And here's my differential equation. db db d time, for some reason I'm leaving a space here, is equal to minus 1 over tau times b minus b final. And this is a constant. And this is a constant. This is the time constant. Okay, so I claim that it would be it would be interesting to me, the physicist, to solve this math equation. Why is that? Well, let's look at this math equation and compare it to this equation that we got from the physics. In the physics equation, dq dt, so q is b, minus 1 over rc, so tau is rc. There's q, that's b, minus c epsilon. Now, what was c epsilon in the physics? If you remember our discussion of the physics of that charging capacitor, the charge on the capacitor Q started out at 0, and then it rose and plateaued, and at late times it was a constant, and that constant was c epsilon. So the final value of Q was c epsilon. That's why I've called this constant Bf. Thinking of this, thinking ahead, this is going to be the final value of B. Okay, so this is a differential equation. This is math. This is physics. And you can see that they're one-to-one related with each other. And now I want to solve this. And the way I'm going to solve this is I am going to put in here minus dBf dt. Now that's a pretty silly thing to do because dBf dt, Bf is just a constant, so dBf dt is just 0. It's a silly thing to do, but it's perfectly legal. I've just added a 0 to the equation. But now you notice that once I do that, I can rewrite this left-hand side as d by dt of b minus bf. And so this is my physics equation. All I did was I added 0 on the left-hand side. It's still my physics equation, written in a math form. And now I compare this to this. And I say, hey, wait a minute. This equation has the same form as this equation. The A here is b minus bf. That means I know how to solve it. There's my solution. So the solution to this differential equation I can get from the solution to the simple exponential decay equation. And it is that b minus bf is equal to some constant. I can pick any constant. I could call it whatever I want. I'm going to call it b naught. E to the minus t over tau. And this, when we do all the decoding and once we figure out how to pick b naught, this is going to be the solution to my physics problem. And it's going to be the end of my math interlude. What do I need to do? I need to pick b0. How do I pick b0? I pick b0 by saying, well, what I want to pick b0, what I want to do is I want to make sure that b at time t is equal to 0 is 0. Because the physics problem that I'm solving was charging a capacitor. The Q on the capacitor started out at 0. B is going to be Q, so B had better start out at 0. So B at time t equals 0 should be 0. Well, B at time t equals 0 should be 0. That means at time t equals 0, I have 0 there. And that means that I have minus Bf is equal to B naught e to the minus 0. That's just B naught. So the way I pick B0 then is I pick B0 to be minus Bf. And so the solution to my math equation is that B minus Bf is equal to this solution where I replace B naught with minus Bf. And here ends the math part of the math interlude, but now I need to connect back to the physics. So this is the solution of this differential equation. It's the solution that I want. Now I need to relate to physics. So when I relate to physics, I'm going to change B back to Q. I'm going to change tau back to RC. And I'm going to change BF back to C epsilon. And so when I go back to the physics, I get that Q as a function of time is equal to, so what do I get? Q as a function of time, that's the B. I'm going to bring this BF over here. I'm going to get BF. What's BF? BF is C epsilon. And then I'm going to get minus BF. That's minus C epsilon e to the minus t over tau. And this is the solution to my physics differential equation, which I obtain after this math interlude. Now, if you want, you can go and skip the math interlude and just say, here's what I say is the solution. You can go check it, take this solution, plug it into there, and make sure it solves this differential equation. But I actually think it's much easier to understand what's going on if you start with a simple exponential decay equation, which I walked you through slowly, but I do expect that many of you have seen exponential decay at some point in the past. And I think it's quite important to understand how this differential equation is related to the one that we actually need the solution to. Once you've done that, here's the solution. So I want to sketch this solution. So this is going to be a graph of Q as a function of time. So Q as a function of time. Q is going to start at 0, and at late times it's going to rise towards the value C epsilon. So I'll put a dotted line here. So Q is going to start here. It's going to rise towards C epsilon. And the time constant plays a very similar role to what we've seen before. Here's tau, 2 tau, 3 tau, 4 tau. Let's look at the solution. When t is equal to 0, Q is C epsilon minus C epsilon times e to the 0, that's 1. So it's C epsilon minus C epsilon. Q is equal to 0. Now what about when t is equal to tau? Then Q is C epsilon minus C epsilon times e to the minus 1. So it's C epsilon times 0.37 of C epsilon. So I've come up so that I'm sort of right about here. And this is 0.37 of that, 1 over e. This is 1 over e of that. Okay, now what about time 2 tau? Time 2 tau, Q of 2 tau, C epsilon minus C epsilon times e to the minus 2. So now I'm up to here. This is 1 over e squared of this. When I go to 3 tau, then I'm up to here. This is 1 over e cubed of this. Sorry, this is 1 over e cubed of this. And now I can sketch the solution for Q of tau. And it rises and approaches this dotted line exponentially. And there's my solution to how a charging capacitor behaves. When you close the switch in the circuit, the charge on the capacitor is initially 0. It starts rising with some initial current. Remember, the slope of this dq d time is the current, so there's some initial current. And as the capacitor starts filling up, the current gets less. The slope of this curve gets less. And once you get to late times, there's no more current because the capacitor is full. And how much does it take to fill this capacitor up? Well, that's C times epsilon. Epsilon is the EMF of the battery. C is the capacitance of the capacitor. So this is the solution to my physics problem. Here it is as an equation. And the math interlude brought us to this solution.